For more than a century, the entire philosophy of railroad engineering rested on a single promise: build the machine strong enough and nothing can hurt the people inside it. Locomotives were rigid fortresses of steel, and every regulation, every design decision, every weld reinforced that one idea: prevention at all costs. But over the past 2 decades, something strange has happened inside the engineering departments of the world's railroads. Engineers studied the data from thousands of collisions and derailments, and they arrived at a conclusion that goes against every instinct of traditional railroading. Perfect prevention is impossible. So now, they are doing something that would have sounded like madness to the men who built the first diesels. They are designing 200-ton locomotives specifically to crash. To understand how radical this shift is, you have to understand what came before it. For most of railroad history, American crashworthiness rules were built around a concept called buff strength. Federal regulations required passenger rail equipment to withstand a static compressive load of 800,000 pounds along its frame without permanent deformation. In plain English, the car body had to be strong enough to resist 400 tons of squeezing force and shrug it off. The logic seemed unassailable. If the structure cannot crush, the people inside cannot be crushed. Except that is not how physics works. Consider what actually happens when a heavy freight train hits something. A load consist of 10,000 tons moving at 50 miles per hour, carries roughly 2.3 billion joules of kinetic energy. That is the energy equivalent of detonating more than half a ton of TNT. A train that size needs more than a mile of track just to stop under emergency braking, which means that by the time the crew sees the obstacle, the collision has usually already been decided by physics. And here is the problem that no amount of steel can solve. When the impact comes, that energy does not politely disappear. It has to go somewhere. It gets converted into deformation, into heat, into violent acceleration. Every single joule. A perfectly rigid locomotive does not absorb that energy. It transmits it. The frame acts like a battering ram, passing the full force of the impact straight through the structure and into the one place it was never supposed to go: the crew cab. Think about what deceleration actually means for a human body. A crash that stops a rigid vehicle over a distance of inches produces forces of dozens of gravities, enough to turn an unrestrained human being into a projectile inside his own workplace, enough to make the control stand, the windshield, and the cab walls lethal. The steel survives. The people inside it, subjected to decelerations the structure refused to soften, often do not. Engineers began describing a grim paradox in the accident data. Making the metal stronger was, in certain collision scenarios, getting crews killed. And there was a second killer hiding in the old design philosophy, one with an almost innocent-sounding name: override. When 2 rail vehicles collide, the massive underframe of one unit can ride up over the coupler of the other and plow into the superstructure above it, the weakest part of the vehicle, the part where people sit. Railroaders call the worst version of this telescoping because one car slides inside the other like the sections of a spyglass. Historically, telescoping accidents produced some of the most catastrophic casualty counts in rail history. A rigid frame does nothing to stop it. In fact, a rigid frame is precisely what makes it possible. It took a disaster to force the first real change. On January 4, 1987, near Chase, Maryland, a set of Conrail freight locomotives ran past a stop signal and rolled directly into the path of Amtrak's Colonial, which was coming north at over 100 miles per hour. The passenger train had no chance to stop. 16 people died, including the Amtrak engineer, and more than 170 were injured in what was then the deadliest wreck in Amtrak's history. The investigation exposed everything at once: a crew that had been smoking marijuana, safety devices that had been disabled, and locomotive structures that offered their occupants very little in a high-energy collision. Within 2 years, the industry adopted a new locomotive crashworthiness standard known as S580. It mandated collision posts, heavy vertical steel members rising from the frame at the front of the cab, designed to stop intruding wreckage before it reached the crew. It set strength requirements for the short hood, the nose of the locomotive, and for the anti-climber structure across its face. Through the 1990s, the railroads went further, adopting the wide-nose safety cab, that big, blunt, reinforced front end you see on nearly every modern American road locomotive. Federal regulators eventually wrote those requirements into law. Fuel tanks were reinforced against puncture because a derailment that ruptures thousands of gallons of diesel turns a survivable accident into a fire. Even the event recorders, the black boxes, were required to be crash-hardened, an admission written directly into the regulations that the machine around them might be destroyed. But notice what all of that still was: stronger posts, stronger noses, stronger tanks. It was the old philosophy, refined: resist the crash. The truly radical idea came from somewhere else entirely, and it required engineers to accept something the industry had spent a century denying. The accident data made denial impossible. Federal Railroad Administration records show more than 1,000 train derailments every year in the United States alone, roughly 3 per day, year after year, decade after decade. Most are minor, low-speed events in yards, but the number never approaches zero, no matter how much technology is layered onto the network. At some point, the researchers stopped asking how to prevent every crash and started asking a colder, more honest question. When the crash happens anyway, who survives it? The answer they engineered is called crash energy management, and it borrows its core idea from an industry that made peace with collisions long ago: the automobile. Your car is not designed to resist a crash. It is designed to die in a very specific, carefully choreographed way, sacrificing its front end to absorb energy so that the passenger compartment stays intact. Crash energy management brings that same sacrificial logic to machines that weigh as much as 40 cars stacked together. Here is how it works on a modern locomotive or passenger unit. Built into the end structures are dedicated crush zones, sections of the frame engineered to collapse at a predetermined force, folding like a precision accordion over a distance of several feet. Crucially, those zones are placed in unoccupied areas, vestibules, equipment compartments, the spaces where nobody sits, so the structure spends itself where it costs no lives. Inside them are components with wonderfully blunt names. Deformation tubes, steel cylinders that absorb energy by being forced through a die that plastically stretches or shreds them in a controlled manner, converting motion into mangled metal at a known, predictable rate. Shear bolts, fasteners deliberately designed to snap at a specific load, the mechanical equivalent of a fuse, releasing components so the collapse sequence can begin exactly where the engineers intended and nowhere else. The genius of the system is that the entire collision becomes a scripted event. The engineers have decided, years in advance, in what order the train will break. Then there is the coupler itself. Federal researchers developed what is called a pushback coupler, a coupler mounted on a mechanism that gives way under crash loads and retracts into the frame instead of acting as a rigid spear. And behind it sits the deformable anti-climber, a face of interlocking ribbed plates on the nose of the unit. When two vehicles meet in a collision, those ribs engage each other like clenched teeth, locking the vehicles together vertically so that neither frame can ride up and override the other. The Federal Railroad Administration spent years validating these two components together, running full-scale collision tests at its Colorado Test Center, deliberately slamming locomotives into standing equipment with high-speed cameras and hundreds of instruments recording every millisecond. The tests confirmed it. Pushback couplers and deformable anti-climbers, working in unison, keep colliding vehicles in line and on the ground, exactly where the crush zones can do their job. In 2018, federal regulators finalized a rule that formally allowed American passenger railroads to buy equipment designed around crash energy management instead of raw buff strength, ending a century of the rigid box doctrine as the only legal option. The design extends into the cab itself. Modern standards require collision posts and corner posts that preserve what engineers call survivable volume. an intact envelope of space around the crew, even as the surrounding structure sacrifices itself. Windshields must pass ballistic and large object impact tests because a windshield on a locomotive is not glass, it is armor that happens to be transparent. Emergency egress is engineered in from the start, with push-out windows and clearly marked escape paths, because the philosophy now assumes there will be a moment after the crash, and the crew needs a way out of it. Does any of this actually work outside a test track? In January of 2005, a Metrolink commuter train in Glendale, California struck an SUV that a man had deliberately parked on the tracks, derailed, and telescoped into other trains. 11 people died. That disaster pushed Metrolink to become the first railroad in America to order passenger cars built entirely around crash energy management, with crush zones engineered into every car end. 10 years later, in February of 2015, another Metrolink train hit a pickup truck abandoned on the tracks near Oxnard and derailed at speed. The new cab car crumpled exactly as designed, its sacrificial structures folding and absorbing the impact in sequence. Dozens of people were injured, and the engineer later died of his injuries, but investigators and the railroad credited the energy-absorbing design with preventing a far deadlier outcome. The steel gave itself up, and people walked away from a crash that, one equipment generation earlier, would likely have been a mass casualty telescoping event. If you find this look inside the hidden engineering of the railroad fascinating, hit subscribe. We break down locomotive technology and the real forces shaping the rail industry every week. Now, there is a deeper question buried in all of this. Why did the industry's honesty about crashes arrive now, in the very era when digital technology was supposed to make collisions obsolete? Part of the answer is that the digital revolution itself made a quiet admission unavoidable. On September 12, 2008, a Metrolink engineer near Chatsworth, California, ran a red signal while sending text messages and collided head-on with a Union Pacific freight. 25 people died. Within weeks, Congress passed a law mandating positive train control across the nation's main lines, a digital overlay that tracks every equipped train and automatically applies the brakes before a collision or overspeed derailment can occur. Europe went even further with the European Train Control System, in which movement authorities are transmitted by radio and an onboard computer continuously supervises the train, ready to intervene the instant the driver exceeds his limits. On a dispatcher's screen, the modern railroad looks fully solved, every train visible, every movement supervised, every human error caught by software. But engineers who study these systems will tell you something uncomfortable. Visibility is not survivability. Digital protection systems prevent a specific category of accidents, the ones caused by human error against the signals. Chatsworth would not happen under positive train control, and that is a genuine triumph. But the software does nothing about a washed-out trackbed, a broken rail, a failed wheel bearing, a truck stalled on a grade crossing at the worst possible moment. And the digital layer introduces an entirely new species of risk. The radio backbone of the European system still runs on GSM-R, a communications standard designed in the 1990s, and its cryptographic weaknesses have been documented for years. In June of 2026, researchers at the Technical University of Munich and Fraunhofer's Cybersecurity Institute published a systematic risk analysis of the European rail traffic management system and concluded that its legacy components, the aging radio network, and the trackside ballasts that tell trains where they are, carry vulnerabilities that persist across every current deployment. Jamming attacks, denial of service, manipulation of data integrity. The systems are engineered to fail safe, meaning a train that loses trusted communication stops. But researchers warn that an attacker does not need to make trains collide to cripple a network. Forcing hundreds of trains into emergency stops across a national grid is a weapon in itself, and the boundary between disruption and disaster grows thinner as the systems become more interconnected. The rail industry spent a century worrying about broken axles. Now it also has to worry about broken encryption. And through all of it, the physical world keeps not caring what the software believes. That is why the crumple zones exist. They are the engineering profession's admission, cast in sacrificial steel, that no digital system will ever make the crash impossible. And that admission leads to the most uncomfortable part of this story, because the same era that gave us survivability engineering also gave us an operating philosophy that makes surviving more necessary. Precision-scheduled railroading swept through every major North American freight carrier over the past decade, and its logic is relentless. Move the same freight with fewer locomotives, fewer crews, fewer inspections, and longer trains. Much longer. Trains stretching 2 and even 3 miles are now routine on American main lines, and government investigators have taken notice. Longer, heavier trains generate enormous in-train forces, the violent push and pull that railroaders call slack action, as thousands of feet of couplers compress and stretch like a steel slinky rolling over grades and curves. Mismanaged or poorly marshaled, those forces can tear a train apart at the couplers or shove cars right off the rails, and federal accident investigators have examined derailments where train length and makeup were contributing factors. At the same time, the workforce that once caught mechanical problems before they became wrecks has been cut to the bone. Employment across the major railroads fell by roughly a quarter in the years after precision-scheduled railroading took hold. Carmen, the inspectors who check freight cars, testified to Congress that they were being pressured to complete inspections at a pace of about a minute per car, a tempo they called impossible to perform honestly. And in February of 2023, a Norfolk Southern train derailed in East Palestine, Ohio, after a wheel bearing overheated and failed in motion. The fire and chemical release that followed turned a small town into a national symbol of what deferred vigilance costs. Put those two trends side by side, and the picture becomes hard to look away from. The industry is engineering locomotives that can survive catastrophic failure at the exact moment its operating model is making catastrophic failure statistically harder to prevent. The crumple zone and the 3-mile train are products of the same balance sheet. One absorbs the consequences that the other accepts, and the people riding closest to those consequences, the engineer and conductor sitting up front in that reinforced cab, understand the arithmetic better than anyone. Their safety now depends less on the promise that nothing will go wrong, and more on how gracefully the machine around them has been taught to fail. So the modern locomotive has become a marvel of sacrificial engineering, a machine designed to die so that its crew might live. The deformation tubes wait inside the frame like folded parachutes, hoping never to be used. And in one sense, this is engineering at its most honest. For 100 years, the railroad promised that strength alone would keep people safe, and it buried generations of crews under that promise. The engineers finally stopped lying to themselves, and the survivors of Oxnard are alive because of it. But those anti-climbers and crush zones also tell a quieter, darker story about the economics running above them. We built machines capable of surviving disaster because the system that operates them has priced disaster in, filed it under acceptable risk, and kept the schedule moving. The steel gives way because the schedule will not. If you find the hidden truths behind the machines we pass every day this fascinating, consider subscribing. We break down the engineering and the unseen economics of the railroad every week. And here is the question I keep coming back to. Do you think technology can ever truly replace human eyes on the track, or are we just automating the risks we used to inspect away? Let me know in the comments, and click the video on screen to go deeper into the rail industry's hidden logic.